Welcome to the Grey Atom YouTube channel. Here you'll get everything from a webinar, student diary, data science Fridays where your questions are answered. Basically, everything that you need to get yourself upskilled in data sciences. Hit the subscribe button, click on the bell icon, have a look at the videos, and if you find something interesting, don't forget to like it. Follow us socially, and we will be there always serving you the best.
I want to welcome everyone who started their Saturday morning with learning about logistic regression, and I'm sure you're going to get the best out of it. So, as I said, today's topic is logistic regression, and the speaker for today is Saurabh Gupta.
Hey guys, how are you all? Can you guys still hear me fine? Just say yes or no on the chat box if everything is cool. Okay, so I see most of us, a lot of yeses on the chat box. So I think we are good from here. So I think Varsha did a phenomenal job to introduce me. I think there's nothing left that I should put in. I just want to say I have a lot of computer science background. I have a computer science graduate degree. I'm a master's in business analytics from University of Connecticut here in US, and I'm really passionate about data storytelling and explaining data science to non-tech business audience. And I think that's why I'm really here today. So this webinar is all about logistic regression, a classic classification example. We're going to learn some concepts about logistic regression and its implementation via SKLearn in Python. So I'm just going to start with the agenda. I'm just going to let you know what are we going to cover right now. So the basic agenda is to let you guys know what exactly is classification, how a classification regression is different via linear regression, and what exactly is logistic regression, and how do we calculate a cost function? How do we optimize our cost function using a gradient descent algorithm? And later we're gonna look at some evaluation metrics for classification algorithms. How do we evaluate performance of a model that we have already built? And in the end, we'll do a live implementation in Python using a Titanic-based data set from Kaggle. So just a little short notice, or like it's my assumption that the people on the webinar have some or little Python coding experience to follow along with me in the notebook. And you guys are a little familiar with, data science and machine learning jargons. Well, if you're completely new and you are unable to get what I'm telling you, you just send me a message in chat box. And if the time persists, I might take up and explain something or the other about the concept that we're talking about. So all good. Are you guys feeling a little bit excitement about the webinar? Oh, okay. So let's just start directly what exactly is classification. So it's one of the supervised learning approach. I'm pretty sure that you guys must know what a supervised learning approach is, where we have a target variable and our data is actually labeled. So to make you understand what a classification is, let me give you like few examples first of all. Suppose we are trying to identify, some emails, a lot of emails, and we want to identify which of them are like spam or which of them are not spam. Or suppose you have an e-commerce online business, you have a lot of transactions and you want to identify which of them are fraud or which of them are not fraud. Or a typical example in a healthcare scenario is to identify from data whether a person is going to develop a tumor in like next few years or not. So in all these problem, guys, there is a very common similarity, which is that our target variable or y is 0 or 1. It's just like yes or no, or like spam or not spam, or fraud or not fraud. It's like binary or discrete in nature. Is it 0 or like it is either 1? So usually we identify something that is 0. It's called a negative class. Suppose in an email example, it would be like not spam. A positive class is denoted by 1, and maybe a spam or a fraud or a tumor, yes, something like that. So whenever in our problem, we just have two target variables, either yes or no, 0 or 1. That kind of a problem is a basic classification problem. It's totally different than regression, where we have a continuous input and we predict something. We're going to see later in this webinar how it differs from a regression problem. So anything which has a binary target variable, anything that can be classified either 0 or 1 is typically a classification problem. Any doubts until now? Any questions? And if you feel anything that is not clear, guys, just put a message in chat box or something like that, and it'll be really easy for me to also let me know that you guys are actually learning or you guys are knowing what I'm talking about. So let's move on and talk about what's exactly the difference between a linear and logistic regression. So just looking here, I have a small plot here wherein I'm plotting like years of experience with salary, and it's a disposition that if you're on a job and as your years of experience keep building up, your salary keep going high, right? So there is kind of a linear relationship between these, and you can actually fit a line here. That's the line I was talking about. It's kind of a line you fit to understand that there is a linear relationship, and you fit a best fit line which has like the minimum error possible. By error, I mean that there is no difference between the actual and the predicted values. So it might have a y of like mx plus c, typical linear regression equation, and we would predict salary from years of experience. Suppose a new data point comes in where we have years of experience equal to 13, and we would be able to say that if 13 is somewhere here, and our salary would be somewhere like here. So this is a typical linear regression problem, right? And that's how we solve it. So going ahead, suppose now we talked about classification problem, right? I just created a random data set here in Python wherein I am modeling a person who has a certain age, and he's going to take a marketing offer. This is a very random example, guys. Suppose he's going to take a marketing offer, yes or no, something like that. So that's how my data looks like. I have a X variable as an age, and my offer is either 0 and 1. So that it is a classification problem, right? Because my Y variable is either 0 or 1. So when we plot this data, it doesn't actually look like a linear regression. So I had few ages here. Suppose a guy in his 20s accepted the offer, he would be on 1, and some guy who did not accept it with some certain age would be like somewhere here. So we actually cannot fit in a linear line to it and say that it's a perfect model. Well, we can fit a linear line to it. Like suppose this is the problem and I fit a linear line to this. There is like two very big problems with this data set. If you fit a linear line to this kind of a binary kind of a data problem. First of all, this line is not correctly representing this data. Most of data is lying here and most of data is lying here, and this line is not doing a perfect job to represent this data. And second of all, suppose if my age is somewhere here and the line goes like this. So if I predict the class, it would give me something here. So that is like greater than or equal to 1. And if my age is somewhere here, it's going to give me the y value of less than equal to 0. This is like totally undesirable, right? We talked about classification problem. Our target or variable is either 1 or 0. We don't want greater than 1 values or like less than 0 values here. So this is not a perfect fit for this kind of problem, so that we can't fit a linear line to a logistic problem. So this is the exact difference between linear and logistic regression. So we would always want our target variable be either 0 or 1, but there are some common similarities between both of these, linear regression and logistic regression. Both of them predict something, right? So linear regression predicts any value. So in order to do this, we have a lot of independent variables. Just like we saw, we had a number of experience, and we were outputting the prediction was also continuous. That means a salary. It could be any number, right? Any real number from 0 to 10,000 or something like that. But in a logistic regression, it just predicts like either 0 or either 1. So our prediction is just, binary in nature, either 0 or 1. And our data looks this similar way, either 0 or 1, something like that. So this is the main difference between linear regression and logistic regression. Guys, any question? Oh, so Vikrant has asked a question. It will be always, so will it be always two options, yes or no, or might be more than like maybe? So Vikrant, to answer this right here, there would always be like a 0 or 1. There's also a multi-class classification problems where you have, more than 3 labels to predict. So you will be predicting 0, 1, or 2, or something like that. Like a type of a car, whether it's a sedan, whether it's a, hatchback, or whether it's a coupe, something like that. So there would be 3 classes or 4 classes we can predict. But that's a different kind of an regression we are not dealing it with right now, but they will mostly be 2, 0, 1. So Chetan asked this question, why is this named as regression though, as it is used for classification? So Chetan, just like it's called regression because we are predicting something, just like in regression here, we are using years of experience to predict something. Similar here, we are using any variables to actually predict the class, so that because of prediction, we actually say that it's a regression problem rather than, it's just a name that it carries the same name from regression problem because we are predicting something, just like that. So is this okay? Okay, so Rashmi is asking another question, whether the independent variables are always continuous. No, Rashmi. Uh, it either in the case of linear regression or logistic regression, your independent variables can be continuous, discrete, classes. We'll see it later in the example where we have continuous variable as well while modeling, and we have independent variables as well. So it can be both of it. All good, guys? Should we move forward, right? Okay, so we just talked about how a linear regression can give us values, greater than 1 or less than 0. Here, if we try to fit this line, so how do we solve this problem? This problem is solved by a logistic regression approach. So now our end goal is to keep our y between 0 and 1, or the end goal should be either 0 or 1, right? So to achieve this, we actually use a logistic function. It's a transformation. It's also called sigmoid function, which keeps our value between 0 and 1. So just look at the plot here. This is a logistic function, or a sigmoid function, it's called, and it goes by this formula. So suppose it would always be staying between 0 and 1. And how does it stay between 0 and 1? Let's take an example. Suppose your t here is approaching positive infinity. So what would happen if you put a t that is like a very big number here. It would be 1 upon 1 plus exponent 1 upon e to the power, a very big number, right? So this would be very, very small in the end, because exponential of a very big number would be very, very small. So it would be 1 upon 1 plus a very, very small number that is very, very, close to 1. And the opposite would happen if t approaches minus infinity. So if you put in this equation, so 1 plus 1 upon e to the power, like, something very, very negative here, it would be 1 upon 1 plus a very, 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 very small number. And that would actually approach to 0. So that this would always stays in these bounds, like 0 to 1. So this function is actually called a logistic function that we talked about. We apply this transformation to our data, to our equation, so that our function should always stays between 0 and 1. So that's the motive of using this function here. Okay. Let me just clear this thing. So guys, this is not something very new, because everyone is talking about machine learning is coming in the picture and all that stuff, but this is a very old problem and old function. It actually came out in like 1860s or 70s, I think. So what exactly do? We had this linear model equation here, right? We had this equation. We applied this sigmoid or logistic function, and we go to this equation. So what exactly is happening? We had this line, we applied this function, and in the end, this function is like this now. So it's at least between 0 and 1 now. And if you remember, this equation on the right hand side, this side actually is a linear regression equation, right? If you remember y equal to mx plus c, this is the same equation. So the right hand side is just like a linear regression. But on the left hand side, we have, so to reach from here to here, we have to apply a log or a probability transformation here. So this says on the left hand side that this is the log odds or the probability of this function. So it literally boils down to something like this. Suppose we are trying to predict something, and the answer that we'll get from this right equation would be a probability value of y approaching to a positive class. So suppose we were looking at this age example, right? Suppose I have this particular x with age, and after applying all the transformation and finally taking the log, I got this answer, that is p of y equal to being 1 is 0.7. This is the output of this equation. This is the logistic regression output, wherein we have probability on the left hand side and the value on the right hand side. So this is saying that the estimated probability of y being 1 is 0.7. So what was y1? Y1 was taking in marketing offer, and 1 was offer, and 0 was they don't take any offer. So it is saying that probability of a guy with certain age X and taking an offer is like 0.7%. Suppose an age is like 23. So we put 23 and everything into this equation and solve for it. So the probability come out to be like, I'm just giving an example, it's come out to be 0.7. So it's a 70% probability that the person with some age X would actually accept this offer. So guys, that's the difference between linear and logistic regression. Linear regression is continuous, and logistic regression would always deal in probability values. So, but we talked about that linear regression should always have 0 and 1 as output. We'll see in next how do we map our probability values to 0 or 1. Any doubts in this part, guys? Anything? Okay, please repeat the last section. Uh, can you tell me, Mukul, where should I start? So by last section, I mean linear regression would always give you a continuous output, right? Some x. And a logistic equation will always give you some probability value. That's the yes, Sachin, we can use logistic regression. There is a multi-class logistic regression uh, model as well. We can use it for a multi-class classification. Yes. So that's the only difference between linear and logistic. Linear deals with continuous outputs, and logistic would always give you some probabilities here. No problem. So I was talking about that now we have probabilities, and probabilities goes from like 0 to 1, right? It could be anything 0.05, 0.75, 0.65, or something like that, right? Oh my, this is getting a little hot, but let me just clear this. And let's talk about how do we limit our probabilities to 0 and 1. So there's a concept called, guys, decision boundary, or you can also call it a threshold. So let me just, so you can call it a you can call it threshold or a decision boundary, which helps us decide whether this class is 0 or 1 based on some probability value. So it goes by the name that, we have to take a lot of consideration here to actually decide on the threshold values. It's a very calculative business decisions. Okay, someone has a, oh, okay, sorry, this is from KATM. I'm really sorry, guys. So we take a lot of effort in actually deciding the decision boundary. It depends on various errors that we'll see later in the session, which you want to reduce. And just to give you an example, suppose here I am setting my threshold to be 0.5. So if my probability of y equals to 1, that is my logistic regression output, is greater than 0.5, greater than or equal to, then I will say this is like 1. This is class 1. Like someone would take an offer if the probability is greater than 0.5. And if the probability of y equal to 1 is less than 0.5, suppose the probability comes out to be like 0.3 something, we would say that this guy wouldn't take our offer. So he's a 0. He's in 0 class. So as simple as that. So we decide the threshold, and based on threshold, we say either 1 or 0. So looking at on this graph, if this is my function, and if I select my boundary at 0.5, sorry guys, if I select my boundary here 0.5, so this part is above 0.5, so everything here would be class 1, and everything here, all the probabilities that lie here would be class 0. So we are using this threshold to decide whether we are 0 or whether we are 1. Okay, I think I have a few questions on the chat. So Vikrant, there are certain threshold criteria that we'll see later in the session. It depends on certain error values that you want to reduce. Typical set is a type 1 error or a type 2 error. Which error which you want to reduce, it depends on that, first of all. And it depends on business as well. What problem are you trying to solve? Do you want your false positive to reduce, or you want your false negative to reduce, or something like that? We will discuss later in this session. So if you guys feeling too much, I'm talking about something errors and something that we have not introduced, just wait and we'll introduce later in the session. So let's just move forward with our cost function. So what exactly is a cost function? So guys, if we make some errors, we want to penalize our model, right? We want to penalize our model of for like, actually suppose if we are saying our model is predicting a class as 1, but exactly the class is 0. So we want to, penalize our model for doing that. So let me just start by giving you an cost function of linear regression. And because right here, our equation was almost linear in nature, like here, but we don't use linear regression cost function for logistic regression, and we'll see it why. So linear equation, sorry, the linear re regression cost function is pretty simple. You have this values, that is the prediction values, and you do a mean squared error where you just do actuals minus predicted. These are your predictions. This is your actuals, and you just sum your actual minus predictions over a number of observations, and that's how you get the mean square error. So in linear regression, your motivation is to minimize this thing, right? But we can't use the same cost function for logistic regression. First of all, why? Because we used this transformation here. Do you remember this sigmoid or logistic transformation? By using this transformation, our probability function, prediction function, sorry, is not linear in nature now. So we can't use linear regression's cost function. Secondly, keeping the math aside, just talking about verbally, if we try to skewer the predictions in a logistic function, let me just focus on this. So this and this. So if you try to do a square here in a logistic equation, it leads to a non-convex function, something like this. It's a very non-convex function. I'll discuss right now what exactly is a non-convex function. So we don't want that thing, guys, because let's see why don't we want all of that. So I just talked about non-convex function, guys. So a non-convex function is a function which has a lot of local minimums. So are you seeing this point here? This could be a minimum here. This could also be a minimum. This could be a minimum, or this could be a minimum, and this could be a minimum. So it has a lot of local minimums. So when we use our optimization algorithm like gradient descent to minimize this thing, it can actually get stuck here on this local minimum and give us the bigger cost. But we want our algorithm to go here. It may or may not find this optimal point because our function is non-convex. So typically, to avoid this, we can't use this cost function for logistic regression. And we would want our convex function to be a very neat function. A neat function is something, a bowl shape function. Just imagine that this function only has like one big spot, one like something like this. If you're going like this, so there's only like one minima, sorry, like something like one minima around here. So this is just like a, your cornflakes bowl. It only has one minima in the center. We would want our function to look something like that. So that's why cost is defined differently for linear regression and logistic regression. This bowl-shaped function, if you have this bowl-shaped function or like something of this sort, this is called a neat convex function, which has only one global minimum. So if we use our gradient descent, it would typically like go in the end here and find this minimum spot for our cost. So these are the convex functions and non-convex functions. So let's go ahead and see how do we actually derive cost for the logistic regression. So right now we have said that we cannot use, sorry guys, again, this is so irritating. We cannot use mean square error that we were using earlier in logistic. We cannot use it. So There's another metric for logistic regression, which is called cross entropy or log loss. So we are saying that we want to penalize our model, and if our model makes wrong predictions, we want to penalize it with a greater value. So just look at this graph. Suppose our y equal to 1. Our true label is y equal to 1. And our predictive probability came out to be like 0.9. So see how 0.9 is like really close to 1. And 0.9 is like somewhere here. So this is the log loss or cross entropy. Look at this, right? This log loss is like very low, like closer to 0. So our cost is 0 here. But what if my y label is 1 and my output probability from the model came out to be like 0.12 or something, or 0.1. So that lies somewhere, 0.1 lies somewhere here. And if you look at the log loss here, it's something infinite. So this function is actually penalizing our model to predict wrong values. So if you predict somewhere here and my real value is somewhere here, this is the value. Look at the log loss. It's like super huge. So we want to reduce the cross entropy or log loss. A perfect model would have like a 0 log loss. Guys, there's nothing like a perfect model in real life. You would never see something close to 0, but you will see something closer, like definitely. We do make predictions very sharp or like very false, but ideally we are striving to make our log loss close to 0 or as minimum as possible, like somewhere here or somewhere here, right? So this is how we derive the cost for logistic regression, and how does our model actually penalizes. Any questions here, guys? Anything that bothers you or that you did not understand? Just send a message in the chat. Okay, I think I have a question. So by penalizing, I mean, Sachin, that if I do a wrong prediction, my cost would increase, and I don't want that. So if I do a wrong prediction, my my model is actually penalizing. So what exactly penalizing means is the cost is getting increased. So Ankur, no, threshold is not kept at 0.5. That was just an example I gave. How do we, divide between classes? And Sachin, penalizing just means the cost that a model has to pay if you do a wrong prediction, right? If something is closer to 1. Okay. Cross entropy or log loss is a same thing, guys. It's just a metric for a cost. It just says cost. So you can say that cost equal to log loss or cross entropy, something like that. It's just like cost. So, and did I answer all of your questions, guys? Ankur, not always at 0.5. We can. Okay, let's just move forward then. I have not included so much maths here because, guys, it's very harder not having a whiteboard and doing all this kind of a shitty labeling on a sheet, and my handwriting is not super good. So if if you want me to do some math, maybe I can send some notes that I have on my notebook or something like that. Okay, let's look at the cost function for logistic regression. Again, clear this thing. Again, select. Okay. So this is exactly how my cost function is defined. Don't worry, guys. I'm just gonna break it down for you. So this means our cost function J has two inputs. First input is h theta x, which is our prediction, and comma yi is our actual. So, and we are taking the cost. Just now I told you how we derive cost. from here, this graph here, right? So if predictions are very far from actuals, a cost would increase, and predictions are closer to actuals, cost would decrease. And we just do a sum on it and divide it by the number of observations. So this gives us the mean cost, like, and we want to minimize this cost in the end. And how does this thing work when we have two different labels, right? Do you remember we have two different labels, y equal to 1 and y equal to 0? Let's just look at this graph and you will understand how we're gonna do it. Well, this graph is pretty much similar to here because we were using a true label 1 here. So just let's look at these graphs right now. So just as Sachin I was telling you, the cost that algorithm has to pay if it makes a prediction this and while actual label is 0 or 1. Suppose my actual label is 1 and I am predicting, this is my prediction, and I'm predicting closer to 1, my cost is like very minimal. Opposite is the case for y equal to 0. If my prediction is 0 and I'm predicting 1, my cost is super huge here. But if I actual value is 0 and I'm predicting somewhere here, my cost is like super low. And here the cost is super high. So that's how we make a trade-off between actual and predictions and the cost. And that's how cost is summed up totally. And we strive to minimize it. It's just, I've just written down everything here. Case 1, when y equal to 1, the output approaches 0. And okay, I think I have a question here. Yeah, okay. And case 2 is when y equal to 0. I just explained you this graph, right? This is my predictions. This is my actuals. And if I predict closer to 0, my cost is minimal. Predict closer to 1, my actual label is 0 and cost is greater than. So we just want to reduce this cost. So if I sum up this function into a one line, this goes something like this. We just added both of the things together instead of having two different things. So see how this is a very compact, because when y equal to 0, this part would cancel out. Sorry, when y equal to 1, this part would cancel out. And when y equal to 0, this part would cancel out. So only at a point, we will have only one equation. Just how we were writing it here. It's just summed up here. When either of the label is 0, one side is going to cancel out. So that's how the cost function is derived. Next is, so guys, any doubts on the cost, how we minimize the cost, how we derive the cost, something like that? Okay, let's just move forward then. So next part is our gradient descent. So guys, gradient descent is actually an algorithm which would minimize your cost. So to minimize our cost, we apply an algorithm which is called gradient descent. So I'm not pretty sure if you guys know about gradient descent or not. Let me just give you a simple intuition and how you can, think very clearly about gradient descent. Suppose you guys are on a hilltop, right? And you are on the top of the hill, looking everything around, and you really want to go. You want to go to the bottom of the hill, or you want to climb down the hill in a very rapid pace. Not rapid pace, but like in a minimum possible time. So what would you usually do? You'll just, look around and see which is the best possible way to go down, right? You'll take a step in that direction. Again, stop, look around, which is the best possible steep, where you want to go, and take another step. And you will just keep repeating the steps until and unless you actually, climb down the hill and you're on the bottom part of the hill. So simply put, that's what gradient descent does. If you start at some point and it will try to just keep reducing your cost going forward. So suppose this is a function I have, and theta is a vector of coefficient, guys. So just like theta 0, theta 1, theta 2 is all coefficients. It's a two-dimension graph here. So, oh wait, it's a two-dimension graph where only we have theta 0 and theta 1. Suppose you you were right, you initialize your theta here, or you were at here at top of the hill. You looked around and you found, oh, this is the good path here. I'm gonna go here. And then you again look around 360 degrees, oh, and you came here. And you again look around, came around, and you finally came here. So this is the minimum point for this graph. So this is what we strive to do. We want to reduce our cost, and this is the cost on the other axis here. So that's how gradient descent works, to be very simply put. So what steps are we actually taking? We need a cost with theta. So theta is just a vector, guys, which will have theta 0, theta 1, how many ever variables you have, theta 2, and so on, like theta. I'm really sorry for the handwriting, guys, but I am trying really hard to do this with mouse. So theta is just a vector of these, and you just initialize theta at some place. Like it could be random. You could initialize at 0, 1, 0.5, anything. And then you look at the other step that I had to take. But the only thing is, how do you decide how big of a step do you take, or how small of a step do you take, or where, in what direction a step you have to take after initializing at this point? So there is a concept of learning rate that comes around here. So learning rate is something that controls how big of a step we take when choosing the next theta value. Suppose we are here, and how down far we can go and how big of a step we can take to reach here. We can skip this and this and we can directly come here. But there are pros and cons of this learning rate. And on every step, we would just keep changing our coefficients. Suppose our, sorry guys, again. We initialize our theta to some value like 0, 1. Suppose we have 3 thetas, or like 0 again. And then we'll calculate some j with this. That is like the cost. And after calculating this cost, we'll use this alpha. That is the learning rate to actually go down a step. I'll just show you in a graph how this works. This is the typical math equation that has to be here. So there is a question from Ekta Shah. She's asking how are the theta values decided in the gradient descent. So Ekta, just like I said, you could initialize theta at you can start anywhere, and gradient descent would actually find you a perfect theta values in the end. So you can initialize at 0, 1, 0, anything, like whatever you think you think that there would be cost, some cost value would be associated with it. You can, set your theta to that. It's just like a very random thing. So let me just suppose we chose this path, right? Suppose we were here, or we were some on other part of the hill, or like somewhere here. Then every part would have some different theta values. I just started to choose this part, and I chose to start over here. So I can end it up here. I would have started somewhere here and may have ended somewhere here as well. So it totally depends where you initialize your theta. Yeah, Vikrant, I'll just show you how do we actually look at how the gradient descent decreases. So I told you guys that when we are taking these steps down, we keep updating our theta values, and our alpha actually decides. Wait, this goes, and our learning rate actually decide how big of a step we take. So suppose this was the theta value here, and this was our cost. Suppose we started off somewhere here, and we are using very small alpha values to actually go down, like 0.000. Suppose I'm using this value, this alpha value to actually go down. So the thing is, if I'm using such a small value, and if I have like 200 odd variables in my model, it would take a little step here, little, and actually come down, like right here. So this process would take a lot of time. So depending on how many resources do we have and how much time do you want to spend on our gradient descent, we choose our alpha values. Secondly, suppose I choose a very large alpha. Suppose we started off here, and if I choose a large alpha, it's a large step, and suppose I came here, and then I came here. But the alpha is too large, it might go here, and then again go here, and again go here. So there might be a possibility that this might never converge, like never. It might or might not reach to a minimum value, but this process would be a real fast one. So we have to trade off between our alpha values somewhere, we have to decide on our alpha values. This is a hyper parameter tuning, guys, and it takes a lot of effort to decide where should we actually start, depending on our data, how many variables we have, and everything like that. So if we start here, we go here, and here we again are change our theta values, and again here. So to actually know that my gradient descent is working, there's one tip. So if I want to know my gradient descent is working fine, my cost of the algorithm, this cost will always reduce with each and every iteration of theta change. So if we keep going down like this, like from here, for every value, my cost would actually go down. So if this is the cost here, with every iteration, if these are the number of iteration, we started off somewhere here. With every iteration, my cost is going to go down. So someone asked in the chat, how do we actually find out that this is the minimum value? The first thing is, if we don't have so much time and resources, we actually look for the point in the graph where my graph is pretty much stagnant by now. So it doesn't even matter if I choose a value here, if I choose a value here, if I choose a value here, or if I choose a value here. But there are like 20 more iterations, 40 more iterations, 100 more iterations here. So I can just choose this value. This would be like my very close to minimum value. I think Gopal Gupta is trying to ask something, but he just sent a backslash. I don't know what exactly that means, Gopal. So I'm really sorry. So we could, plot our cost function with the iterations and see where are we right now. And we choose our theta values here. So these are my final theta values, which would minimize my cost. That minimize my J of theta. So this is our like final. We could choose anything somewhere between here. That is pretty much fine, but we don't want to waste our resources after, like 5 iterations. Even the cost is going like this. It's never going to go like downhill. So we could take anything somewhere here. Yeah, Seema. So Seema is asking in question, guys, what if we reach to the local minima? Yeah, that's the point actually of gradient descent, to reach our local minima point. So that's the where our algorithm would work fine, and we would know how it converges. That's the end goal of actually, to get to a local minima point. Not even local minima, but like global minima, sorry. So Deepak is asking, if we choose different theta values, we may reach different local minima. How to get global minima? So, okay, let me just go back here and show you guys this graph. I told you, right, why we are not using this cost function, because we have a lot of global minimum here, sorry, local minimums here, right? But the function that we are using right now is a convex function. So this function, cost function, is actually a convex function. So it would only, have one global minimum, not multiple local minimums, because we eliminated this part of local maximum by taking a simpler bowl shape curve rather than this. So that's why the reason we were not using this equation to minimize the logistic regression, because we would end up in many local minimum. That's the reason we are using a neat convex function here. So that's the answer, that we would never end up. So in this is a very neat convex function. So this is the minimum, like this is the minimum. So we will always find a global minimum point in this kind of a graph. We are not dealing with this kind of a graph right now. So yeah, that's how it works. Okay, guys, any more questions? Let me just move forward to the evaluation metrics of a classification model. And the your questions about threshold and how do we select a threshold would be really answered here. Let's go. Okay. So evaluation metric is something, suppose we have built a classification model now. So guys, Seema is asking a question. In a case where we don't have a convex function, we cannot use logistic regression, right? So Seema, we actually by using this cost function here, this function, we actually, transformed our this graph to this graph. So this graph would always have a local minimum, global minimum, sorry. Yeah. So if we use this cost function, I mean to say, if we use this cost function, we would always end up in a global minimum point, because our function looks like this, not like this. Okay, guys, let's just move forward to the evaluation metrics. Oops. So evaluation metric is something. So we built a logistic regression model now, and how do we, evaluate the performance of a model? How do we say that, oh, my model is doing good, or my model is doing bad, or something like that? So the first thing here is to, finalize the threshold value, because threshold value will actually make a difference, because if we choose a different threshold values, the errors would change a lot. So the election of this threshold value actually depends on two types of errors right now. Those two types of errors are false positives and false negatives. Let me just explain you what these kind of errors are. So to reduce these errors, we choose different threshold values. What value, how value, let's just look at it right now. So what exactly is a false positive? Suppose in your data, your actuals were like 0 label, and your model says, no, this is not 0, this is 1. So this is an error, right? Actually, it's the label is 0 and model says 1. This is kind of a false positive error. My model is falsing on the positives. And this is also known as type 1 error. And second error is false negative, wherein in actual data, my label is 1, but my model says, no, it's 0 when we predict. So this is a false negative error, or it's also known as type 2 error. So to reduce the errors, we use different threshold values. And let me just give you an example, right, real quick, so that you understand how do we choose these threshold values. So guys, first example is just listen to me carefully here. When suppose we are treating patients. So we built a predictive model to, to develop, to predict that someone in the later 10 years would develop a heart disease or not. And so one is my that he get the heart disease, and my zero is no heart disease in next 10 years. We made some this kind of a model. What do you think? What kind of a error we want to reduce here? Can anyone wants? Does anyone wants to try? What kind of a error we wants to reduce here in this kind of an example? So okay, I think no one wants to try. So let me just go ahead. Yeah. So BDM says false positive. Ankur says false negative. Someone also says type 2. So guys, uh, here we want to reduce our false negative error. Why? Look at this why. So if someone who is going to have a heart disease in the future, but the model is saying, oh, no, he's fine. There's no heart attack, heart disease for this guy in 10 years. This is a disaster mistake. We are telling someone that you're not going to have a heart disease when he's going to have a heart disease, right? This is a tremendous error. This is a false negative error, and we want to reduce a false negative in this scenario. So what we'll actually do, we would increase the threshold or we would decrease the threshold. What will we do? Anyone? So we would actually, decrease the threshold here. So like instead of keeping threshold to be 0.9, like very strict, I would keep my threshold to be like 0.7 so that my model is not very strict and doesn't make too many false negative errors. So this is one case. Let's look at the second case right now. You remember the spam, not spam example? Yeah. So class 1 is spam and class 0 is not spam. What do you think? What kind of error we would want to reduce in this kind of a scenario? Anyone wants to try? Okay, so in this kind of a scenario, we would actually, so someone answered, let's see. Yep, Girish, PDM, everyone says false positive. Yep, Rashmi says false positive. Yep. So in this kind of scenario, we would actually want to reduce your false positive. So what exactly was a false positive? The false positive was that we predicted the message was spam and it going to send to the spam folder when it was actually not spam. So there was an important calendar event that went to your spam folder. This is the mistake that we don't want to do. Otherwise, if spam folder come into your inbox, I know this is a little annoying, but you can always delete it. But what if your big meeting calendar event went to your spam? So this is the kind of thing where we want to reduce the false positive error, and we would actually make the threshold to be very strict, like 0.8 or greater than that, depending on our problem, so that my model doesn't make any mistakes on false positives. So this is the first thing, we set the threshold. All clear, guys? I think we have like another half an hour. I think I need to really quicken up. Okay. I just had a quick question, guys. Do you guys mind if the webinar gets extended to like 10 more minutes or something? Because we might miss some content and I would really want to give you the full picture of logistic regression. What do you think? Just write it on the chat box. Okay. Well, if someone has anything urgent or they don't want to be, I can share this notebook to your email ID via Grey Atom, and you can actually follow along later as well. So totally depends on you guys. Like, okay, let's not waste time and go ahead. So setting a threshold is one thing. Second thing that evaluates the performance is a confusion matrix. Don't go by the name of confusion. This is not confusing at all. It's a very simple thing, so don't get confused. So it's just a table layout of the errors that we were discussing right here. We only discussed two major errors, false positive and false negative, that we want to reduce. And there are two more metrics called true positive and true negative as well. So just look at this box right here, guys. You don't need to look somewhere else. Just focus on this box, and let me show you. This box right here. This is a confusion matrix. It has an actual label and a prediction label. So usually and we have some matrices called sensitivity. It is also known as recall, or like true positive rate, which goes by the formula of this. So this is true positive over true positive plus false negative. That means the proportions of true positive which are correctly identified. So this thing, like this upon this whole thing. And there is a thing called specificity, which is a true negative rate. So we just discussed true positive, and the true negative would be true negative upon true negative plus false positive, like this one right here. And there is this accuracy. So what exactly would be an accuracy? So if our model correctly identifies zeros and zeros and ones, so this guy over the whole matrix would be the accuracy thing. Don't worry about these things because these are similarly derived from this table only. So these are the main matrices that we follow: sensitivity, specificity, and accuracy. Okay. So this is a one way of looking at, and we discussed our threshold up. So we would either want to reduce false negative or either want to reduce false positive. So we want very less number of observations here in both of the boxes or any of one of the boxes, depending on our problem. Next classification metric is a ROC curve. So nothing very special about this curve. This curve is just visualization, a plot of sensitivity that we discussed right over here, right? And 1 minus specificity. So if you remember, sensitivity was true positive rate, and if you do a 1 minus specificity, it would be false positive rate. Let me just show you this right quick. So this is a very random model that's here. I'm not talking about. Ideally, what do we want, guys? We want our false negative to reduce and our false positive to reduce, right? So ideally, we want our sensitivity should be really like 1, and our specificity should be 0. So we want our curve to look somewhere closer to this point, like this point right here. So if something goes like this, so this is a pretty good model right here, right now, because we are reducing false negative here and we are reducing false positive here as well. So we want our ROC curve to be as close as to 0 and 1. That's the only purpose of looking at the ROC curves. So let's go ahead and see another metric called AUC. AUC is nothing, is just the area under the ROC curve. So area under this curve somewhere here would be the AUC. And AUC will be always between 0 and 1 because area under the curve is always between 0 and 1. So the better this metric is, the better your model is performing upon the normal baseline or the regular model. So if you look here, I want okay, let me just show it to you. I have a few questions in the chat. Give me a second, guys. I'll just take these questions right away. So ideally, I would want, this is also a pretty good model. Like I would want my ROC to look like this. And the area should be like fully uncovered, like somewhere here. This is just an area under the curve. So okay, let me take the questions on the chat. Oh, okay, there are no questions. They are only saying, okay, we are good. Okay, so this is in metric called AUC. Yes, so Vikrant is asking this question. The higher the value of AUC means the model is performing good. So let me give you an intuition about what does AUC exactly says. Suppose we have two random examples from our data set. One is a label 1 and the other is a label 0. So AUC of this 0.775 means the probability of y equal to 1 over probability of y equal to 0. That means the ratio of getting a positive, y equal to 1 probability over ratio of getting y equal to 0 probability is just 0.775. That means y has a chance that it has this into multiply the probability times. This is just a ratio metric. So it says in most of our cases, our model would be able to perform, divide our y 1 and 0 in 77.75% of the cases. So that's what it says. So if you take a normal model that's simple, a yes or no, a guess between 0 and 1, what would the probability be? Will be like just 0.5, right? 1 over 2. So if our model is actually giving us number greater than 0.5, that means this is a smart model and actually is doing some work to distinguish between these classes rather than just taking the average of 0 and 1. This is exactly what an AUC means. Area under the curve. Perfect. Okay, let's just clear this stuff up. Okay, guys, any question here? Area under the curve. I can share you this notebook with you. It's in the Jupyter notebook. And you can follow along on your personal laptops. You just need a few Python libraries installed, and that's it. It's just a very simple notebook. You can just follow along. Maybe people from Gear Atom will just send you this. Okay, so next is the interesting part. I think most of you would really want to look how do we implement this in Python using a library called SKLearn. SKLearn is just a simple library. I shouldn't say simple. It's a library in Python where we have a lot of like almost every model where you don't have to write code for every model, but you can import the libraries and actually solve for your problem. So whenever we have a data problem, guys, there is a simple workflow structure that we follow. Okay. So guys, BDM is asking a question, any way to gain higher accuracy using logistic model? Well, BDM, it really depends on a lot of things. Accuracy really depends on how your threshold is, what are good variables do you put into your model, and it depends on a lot of things. So yeah, you can get higher accuracy using logistic model if they have a linear relationship. Definitely yes, but there are a lot of ifs and buts involved in getting higher accuracy. So yeah, I hope this answers your question. So a simple structure that I like to follow is to, understand the problem definition really well. This is really important, guys. Mostly on your on-the-job training or something like that, learning about your problem, what exactly a problem you're trying to solve is pretty important. In academic purposes, it's a very clear understanding that, oh, we're going to solve for this. We want to classify this. But in a very business case, this part really needs big understanding of the business. Next is you just go and acquire data. You just do some pre-processing, clean the data, look for missing data. You don't want any missing data or any catches in data. Look for outliers and stuff like that. And then is the exploration of your data. You just explore your data with your Y variables and look at the patterns, what goes well into the model, what doesn't go well into the model, what all variables you can actually put in and stuff like that. And in the end, you just use SKLearn to model all that stuff. So let's just start with this. First thing we would be doing is importing the libraries in Python. Okay, I have a question on the chat. Sorry, guys. So PDM, let's just keep your question for higher precision or recall in the end. I'll answer it in the end. It really depends what exactly do you want. Do you want high precision or high recall, or you want a balance of precision or recall in your model, and then you use a F score that I have not shown in here because it takes a whole new lesson to understand how precision, recall, and a F score works in a problem. But yeah, it's a mix and match. You would somewhere, if you want a decent algorithm, you would want something that's a mix of precision and recall. So you wouldn't want such high recall or such low precision, or like very high precision or recall. It totally depends on what problem you're trying to solve. And it's just like, these are inversely related. If you try to increase precision, the recall would decrease, and if you try to increase recall, the precision would decrease. That's how it is. It really works. So yeah. Okay, so let me just, here is the simple code for importing the packages and libraries. I'm using pandas. This is a very good library for a better take on data structures in Python. And then I have NumPy, it's numerical Python, and then data visualization libraries, matplotlib. Cvon is a really nice library for data visualization. I'm setting some styles, importing warnings, and in the end, I'm just using sklearn and importing preprocessing. We would import some other modules as we go forward into the data. So guys, the data we are looking here is a Titanic disaster data set. I'm pretty sure this is a very famous data set, so most of people would have heard about it. So I have training and test data, and what I'm here doing is just fetching data using the read CSV function from pandas to actually get the data into a data frame, and I'm really combining these data here together. So let's just look at our problem definition and look at the data first. So I'm just looking at the column values. There's a column values function which shows you all the columns where you can see what our columns are there in the data set. And there's a head function. So this is my train DF that I used here. This data frame has all the data, and I'm using the head function to see the top 7 rows. So let's see what the data is all about. So all the passenger who was on board on Titanic, and there's an information about who survived and who did not. So our variable of interest or target variable here is survived. So look at here, we have supervised learning problem because we have label data. And secondly, our survived is either 0 or either 1. So we have a classification problem at hand. Passenger IDs are just IDs for people. Survived is a label for if they survived or not. P class is something on which class they were on board, like class 1, class 2, class 3. I think just like airplane, it's like business class, coach class, something like that. The name of the person, whether he or she was a male or female, what age was the person was. SIBSP is a column which says whether this guy had any siblings on board or not. So 1 means they had one sibling on board, and this column talks about if they had parents on board. So this guy was just pretty much maybe was there with their brother or something. There were no parents on board. This is their ticket number and how much fare did they actually pay. The cabin is which cabin they were in, and embarked is something where did they board the ship. So either they boarded in Southampton, Queenstown, Usherov. These are the 3 boarding stations for the Titanic ship. So we've understood the data. Let's just to investigate. First thing is to investigate the data types of our columns if we want to change, and just make sure, guys, your training and testing data type should match. There should not be any mismatch in the data type. This is a good practice to ensure that your training and testing data match. So their data types match. So just looking at the info here for the different columns. Passenger ID is integer. See, sex is an object. Object means it's a class like 1 or 2 rather than it's a factor. There's an integer. The fare is in decimals, so float. Cabin is also a class, and same data types are for uh, testing data set. So I'm using a describe function. This is a pretty good practice first, before even digging into the data, where you can actually see the summary statistics for all the columns. But make sure describe would only show you statistics for all the integer columns. It wouldn't show anything for the object columns. So see, the cabin is not here, or embarked is not here in these columns. Pretty good observations. You can look at the summary and have some observation about the data. So some observation I found out was the mean fare was around 32, and there were people who even paid $500 fee for being on the Titanic. The mean age is like 29, pretty much almost young people on the cruise. And I just figured out that P class should be here categorical instead of, we can change this later on. And if you want to see the summary stats for categorical or object variables, you use a include a parameter here with O, which will show you all the object variables. So sex has 2 unique variables, ticket has 681, cabin has 147, embarked has 3, Southampton, Queenstown, and some the other one. And these are all the frequency that saves. Next part is looking at our survived variable. We really want to ensure pretty much sooner we dig into the data that our survived variable is pretty much balanced. Looking at it, it's decently balanced. I'll say I can go ahead with this data. But if our data is imbalanced, suppose we have all the zeros and 1s are like very few somewhere around here, we would have to do some transformations to actually fit this kind of data. So after doing preliminary statistics, let's move forward and look at the missing data part. It's a very simple thing. I'm just using is null sum function to actually denote the missing data here, and it's just showing me in every variable how many percentage of data is missing. So see, cabin has like 77% missing data, and if you recognize from here, cabin was something, a category, right? So to treat this is an NaN here. NaN means null. So treat this, we can actually not treat cabin. We cannot impute anything for cabin because we don't know, right? So we would just drop this from our data set. So I really dropped cabin because we couldn't impute anything. Next was age. Age has like almost 20% data missing. I think I have a question here. So Sachin is saying, should we not use fare to impute cabin? So yeah, Sachin, you can actually do that, but see, look at this. Out of 891 total observations, 687 of them are missing. So we don't have so what was, let me just revisit the question. So he says we should use fare to impute cabin. Like I don't understand, Sachin, how would you exactly use fare to impute cabin? Cabin is a categorical variable, right? So this NaN should be filled by something C123 here. We cannot randomly fill anything into cabin, right? Even using fare. So you're saying we use this fare because everyone could have paid a different fare. I'm not sure about that. So yeah, we could do that, but that require more analysis on the part. I'm just showing you the basic workflow and structure. How do we go ahead in doing some EDA, exploratory data analysis and model. Next, we are using just uh, fare. So Vikrant is asking which fare will be fixed right for each age group. I'm not sure, Vikrant. Suppose it's not about the age group. If you book a flight, if you book it pretty soon, you get a good deal. If you book it very later, you don't get a good deal. You have to pay heavy prices. So it can be something like that. So see, these are questions you really have to look in the data and analyze that for. Because I didn't have much time here, so I did a basic analysis, and I'm just walking you through the structure of analysis. And let's just go ahead with what we have done, and I'll take your questions in the end now. So age has almost like 20% missing. So I'm just looking at the age variable here. The distribution looks positively skewed. So either I could use mean or median to impute, but usually we wouldn't use mean because it is affected by outliers. So I'm just going to use median to impute all the.
1 second, I couldn't find distribution looks in your.
I'm really sorry about that, guys. So I'm just going to use my median to fill it. See, there's not much difference. The mean age is 29, the median age is 28. So I'm just going to use our median age to fill it. And next is we do have, look at here, we do have some embarked missing. So to observation doesn't have embarked. So let's see where did the people embark the most. So most of the people here embarked in Southampton. So I'm just gonna impute, these two missing points with Southampton because that makes sense because most of the people just boarded in Southampton. So looking at the imputation here, I am filling age with median, filling embarked with a maximum value count that is Southampton, and I'm dropping cabin because I couldn't impute cabin, right? So now if I run the same thing again, I don't have any missing values in my data. And the data looks like something like this. Okay. So now someone was asking in the someone was asking before, can we use categorical variables or just use continuous variables? So we can use both of them, but it makes sense to make dummies out of your category variables. I'll show you in the later why we actually use the dummy variables. So this is a simple pandas method where I'm telling that in my train data for these columns, just make dummy variables. Dummy is just like this, guys. So for p class 1, if a p class is 1 is 1, there would be a 1 here. So if the p class was 3, the 3 has 1 and both of them has 0. And if someone embarked at Southampton, it would have 1 and both of them would have 0. So I'm just getting dummies for these three variables. And because sex would have done 2 different dummies, so I just remove sex female. Passenger ID is not needed in our data. I'm just gonna remove passenger ID, dropping it. We are not requiring name, and I'm also dropping the ticket because it doesn't tell us something about the data. So final training data looks something like this right here. We have survived, age, fare. The cabin is gone, ticket is gone, name is gone, passenger ID is gone. That's it. Okay, someone has a question here. Yep. Just funny, one hot encoding and dummies are just same. It's just a different name used in the terminology. They are both of them are same. So guys, Javini asked this question, is getting doing dummy data is same as one hot encoding? Yes, totally yes. So one of the good practice is that whatever transformation you apply to your training data, you should also apply to your testing data. So I'm just looking at my testing missing values. Age has some missing. See, even fair has some missing here. There was nothing missing in fair in training data. So we have to impute something. Cabin is missing. So I'm just gonna impute the same stuff that I did with training to test. Age with median, embarked with Southampton. I'm just using fair median because training didn't have anything. I'm dropping cabbing, making dummy variables, dropping sex female, passenger ID, name, all ticket, all is dropped. And this is how my final training data, sorry, I'm really sorry, testing data looks like. And if you check for missing variables here, and there's no missing variables. Okay, someone has a question. Okay, next we move on to the data exploration part. Here is this part where you get to know your associations of your y variables to your different x variables. So I'm just using a simple visualization from Seaborn. Here it's a kernel density plot for age and the one who survived and one who did not survive. So just look close here, guys. The distribution for age looks pretty much similar, but there is a huge bump here. Looks like the children, the young children less than 10 years of age survived more compared to the ones who are here. And let's look at the fair. These distributions are totally different. Just look how it looks like. So people who paid less fair here are more probably to die, and people who paid more fair are pretty much, staying or surviving. Next, we move on to the passenger class. Who survived in what passenger class? So pretty strange, guys. People who are traveling in first class, they survived better compared to the people who were in second or third class. Next, we look at some other variable here, and embarked. People, I don't know why embarked would actually make sense. I don't know, but most of the people embarked at Southampton. But people who did embarked at Cherbourg were the one who survived the most. And this is the most interesting part here, guys. Look at females survived more than males. So I think people who were saving the people on Titanic ship who were saving people were actually make sure the females and the small children were prioritized in actually saving. So this is an interesting observation that would actually help us to model our data well. So next part is just implementation of logistic regression and results. Let's see. So I'm gonna from SKLearn import logistic regression, some of the other metrics, train test placed, validation score, accuracy, the metrics we were talking about in the concept part, classification, precision, recall, confusion metrics, all of this thing I have imported. Okay. I'm really sorry, guys. Next, so when we are modeling in Python, our x's and y should look like this. My x should have all the independent variables. So I'm dropping survived variable here and putting all the other variables in x. And my y is just, my label survived for the whole data. That's it. And there is a very interesting function from sklearn called train test split. this function would automatically split my x's and y's here into a training and testing split. So my testing size should be 20%. That means if I have 100 examples, 80 would be like training and 20 would be test, and I'm sending a random state to so that I could replicate the results later on. So now to make a logistic regression, I just import logistic regression from a linear model, and I'm just giving logrex any name to a logistic regression function. And this is the main important part here, guys. Logrex.fit x train y train. This is what it is doing. It is fitting that sigmoid S level function, S shaped plot. You remember that when you were talking on the concept, it will fit it on the train data. And after fitting, we can actually predict on our test set. So we train on our training data and we predict on our test set, so that this data is actually not seen by our model. So this would be a fair evaluation metric. So by default, logrock.predict would actually give us binary variables 0, 1, and that's what we want, right? But if you want to look into the probabilities values, there is another function here called predict probabilities, where you put in your X test, and this would give you all the probability values. And if you want to look at the coefficients, we just do a dot coefficient from the model, and this would throw us all the coefficients. But I really want to know, right, these coefficients associate to what feature. So I just created a small data frame here with features, and I'm just, combining both of them together to actually look at the feature and coefficients here. So look here, guys, just how we were exploring in our EDA process. P class equal to 1 has the highest coefficient. That means this variable contributes the most towards predicting y equal to 1. And then there's P class and someone who embarked at C, and that's the thing. And you remember how males were not surviving? Look at this. The sex male is actually a negative coefficient here. So this is actually contributing towards P of y equal to 0. Anything that is positive here would contribute towards this, and anything towards that is negative here would contribute towards y equal to 0. So we can get to know that if someone has to survive, he should be in class 1, he could have embarked in C and would have paid a much higher fare, and rather than, someone who's in older in age, less likely to survive, traveling in class 3, less likely to survive, and a male, very less likely to survive. So this is the total how we are interpreting this coefficient for a label y equal to 1 and y equal to 0. So I think, okay, so Vikrant asked this, what is the random state? So Vikrant, this random state is just like a random seed that we said. So if I do this again and again and I want to replicate the same results, I would just send a random state to 2 or any other integer value. I could do 3, 4, whatever. But if I don't specify the random state, my results would change. This split would change all the time, and every split would have a new model and they would have some new accuracy. So to replicate the results again and again, we set the random state. So we talked about our coefficients here. Next, we remember the metrics here. First was the confusion matrix. So it's just a confusion matrix of y test and the y predicted that the model spit out. It's just a normal guys plot where I'm showing these true positives, true negatives, false positives, and false positive. And we haven't decided on the threshold here yet, but we can decide based on the problem. And I don't know how to decide threshold for this. Maybe we could choose something and then decide. So this is how the confusion matrix looks like. Look at this. false positive 9, false negative 30. And if you want to look at the accuracy, so you do true positive, true negative divided by this whole thing. I've just given you some metrics here. Sensitivity or recall was true positive upon true positive plus false negative, and specificity was something true negative upon true negative plus false positive. So that's how it is. We can calculate these. So our recall is coming out to be 0.62 and specificity is coming out to be 0.91. So let's see how we go forward with and look at the real metric, that is the ROC curve. You can do a classification report from SKLearn, which would actually give you the precision recall that someone in the chat was talking about. Okay, guys, we have to wrap up in like 10 minutes, so I'm just gonna skim through the ROC curves here. So the metrics I'm gonna use here are accuracy score. You remember log loss, right? This is the cost of the function, and AUC. So these are simple. I've just derived this from SKLearn, and I'm putting my testing data and my output. This is my actual. These are my predictions. I'm just using that and calculating log loss using the y-test and the predictive probabilities. You remember log loss, right? AUC, just like similar true positive and false positive rate. So if I just use this in this, and this splits me out this result. So the accuracy of our model is like 78. So we are doing pretty good, I think. This is a pretty basic model. We haven't even done much of a feature engineering or something. Log loss is 0.50. Maybe we could reduce log loss a bit. And the AUC is 0.833. So it's very much greater than 0.5, right? 0.5 is the baseline model. We are doing pretty good, guys. So let's look at the ROC curve here for this model. This is the baseline, and my ROC curves looks like somewhere around here. And the area under ROC curves is 0.83. You remember how I want my ROC to be somewhere here? So if my model would have been somewhere here, I would have been really super happy. And if it would have been like somewhere here, I would have been jumping off my bed right now. So we are using all the variables, no feature engineering. Still then a pretty good decent model that we have here. And the area under this curve is like 0.883. So we have made the performance metrics, seen how our ROC is doing, how our AUC is doing, everything. And to make final predictions, we just, on our test data set, we just do a log reg.predict, just like earlier thing when we were predicting on our test set. And this is the final test set. We are just going to do log this.predict. And this is going to give us like the labels for 1 or 0 in the end. So this is my final test sample data, how it finally looks like. Let me show you one more time. So we had all this data and we actually have now survived. So this is the test data, guys, that Kaggle had given me. So I don't have real label into this, so I can't check how well I'm doing. But looking at this ROC, I should be doing somewhere around this point. Like I should be doing somewhere around 0.8 or something like that. So that's how a logistic regression is implemented. If I had a little more time, I would have gone a little more detail. But now I'm like totally open to questions, something, and we'll wrap up then.
That's great. Thank you so much, Saurav.
So there's a question from Deepak Thandra here. He's asking what is the difference between log loss and accuracy, and which is the best metric. So Deepak, if you remember log loss from our concept, it is just cost. Log loss is not a metric. We can't compare log loss. But accuracy is a metric we can compare. So give me a second, guys. Someone from Gatom is really calling me.
Thank you so much, Saurav, for this amazing session. I think we're open to Q&A and we can extend it for the next 5 to 10 minutes. So please, guys, who wish to pop their questions on the chat box, please feel free to do that. And also make sure you fill the feedback form, because that's how I will be having your email IDs and I can definitely provide you with the notebook that Saurav has helped us with, as well as the presentation. I mean, the whole lecture will be available on the platform within a week or two times. So please make sure you fill the form and let us know about your views on the entire session that Saurav has taken for us. And please go ahead. Do not feel free. Do not sorry. Feel free to ask any questions regarding the whole session. Thank you.
Yeah. Okay. So, guys, let me answer a few questions that you guys have. Okay, so I was answering Deepak's question here. So the log loss was something associated with the cost. So when we have to compare the cost of a model, when we are doing different iterations, we do log loss. And accuracy is something that we can compare between models. Suppose you have a logistic regression with 15 variables and a logistic regression with 30 variables and a random tree or like a decision tree, and we can use accuracy to compare. Is that okay? But exactly, in a logistic regression, accuracy is not what we seek for. We would want to look in to precision and recall and would want to decide which one do we actually care for more depending on our business problem. So if you want to, decrease the false negative, we would increase our recall. And if you want to decrease the false positive, we would increase our precision. So that's how it is. So there is a balance that we want to strike, and accuracy is not the best metric we should use. Did I answer your question, Vikrant? So usually we compare models via AUC rather than accuracy. So if you have a good AUC, because AUC is a balance between your recall and a false positive rate. So if a good AUC you have, the better the model is. Okay, so Anurag has here a question: how to use continuous data as log model? Anurag, can you be more specific? I actually don't understand your question. What you're trying to say? Are you trying to say how to use continuous data? I'm really sorry, I can't get this. Can you be more specific? Hey, Girisa, I'm really sorry. I see what you have been trying to do, but I'm not really sure of what course is. I think Grey Atom has a wonderful course designed by all the data science mentors that they have. So maybe you should look at their course. If this webinar really helped you, I'm even a beginner mentor. There are beautiful mentors in this program, and they would be definitely able to help you and give you some personal attention as well. So I think we should take up this course. So Sachin is asking a question: does logistic regression understand numerical variables? So Sachin, let me show you why actually we did one-hot encoding. So if you see here, my feature and my coefficients, if I don't do one-hot encoding or dummy here, all of my features wouldn't have a coefficient associated with it. So if I do if I have like, let me show you. If I have like 3 classes, like P class 1, P class 2, P class 3, my coefficient would only show up for 1 and 2 class. And I have to do 1 minus coefficient of 1 and 2 class to actually got the coefficient of third class. But if we do a one-hot encoding, we could actually see coefficients for each and every class right here. We don't have to, do this math. So that's the only benefit for one-hot encoding. So Sachin, did I answer your question? Okay, next question I have from Anurag is Anurag is asking questions that he has a variable which is continuous in nature and I need to use a logistic model. So do I implement? Yeah, Anurag, you could use continuous or non-continuous, anything, any functions as your independent variables. This wouldn't change anything. So look at this here. The fare variable is continuous in nature, right? Age variable is continuous in nature. So yeah, we can use those. There's no problem with that. So Ankur is asking one more question, guys. How do we confirm that linear relationship exists among dependent and independent variables in classification problems? So Ankur, to answer your questions, we actually, when we were doing EDA, the exploratory data analysis, that will actually tell us what kind of relationship do we have between the independent and dependent variables. Let me see if we have something here. So, well, Ankur, we have to do some EDA to understand how is the relationship between dependent and independent variables. Definitely EDA, you would get to know. And if you have all the numerical variables, you can do a correlation. In simple terms, you can look at the correlations between two variables, and they will tell you if you have a positive correlation, you have a linear relationship. If you have a negative correlation, then also you have a negative linear relationship. So Deepak is asking, can I share the notes? Yeah, Deepak, why not? Sure. I do have the maths notes on my notebook, and well, I can share with the Creatum guys, and I think they're gonna just send it to your email or how they're gonna do it, because this notebook will be available. So also Giovanni is asking one question: what should be the best score for F1? I mean, for the best model. So Giovanni, F1 score is something like an harmonic mean. So F1 is 2 into precision and recall upon precision plus recall. That's the F1 score. So this is a pretty much balanced score between precision and recall. So usually you want your F1 score to be between like 0.40 to 0.60, because precision and recall are like totally, uh, different. I mean, like inversely related. So if you try to increase precision, the recall would decrease and the opposite would happen. So a good F1 score would be somewhere around 0.5 or like 0.6, 0.7, maybe 0.45, something like that. Okay, guys, do you have any more questions now? Well, it was, if I'm still waiting, if you have any more questions, I can still answer. If not, then yeah, it's a Friday night here, guys, in US. I need to go and chill out. No problem, guys. Thanks a lot for actually being there. And I know it's a Saturday morning at 9 a.m. I hope you guys were not hungover. Hello?
So I think this was a great session. Thank you so much, Saurav. And I'm sure all the guys have definitely enjoyed it. And I will let you know what they think about the entire session through the feedback forms. And I will definitely send a collective view. So I think that's pretty much it. Guys, if you feel to connect, like feel free to connect with Saurav on LinkedIn. So you can do that. You can search him, Saurav Gupta at Nordstrom, and you shall definitely find his LinkedIn profile. As well as if you have any questions or you have any other thoughts on how the session should be better or anything, please feel free to write to me. I'm at varsha@greyatom.com. And that's pretty much it. I would really like to thank you, Saurav, for such a wonderful session and for definitely spending your Friday evening with us. And I'm sure you're going to enjoy further. And that's great. I think that's pretty much it from our end. And feel free, if you would like to hear more of Saurav, do let us know on the feedback form. And yeah, that's pretty much it. Thank you so much for your time.
Okay, guys. Thanks a lot and have a happy weekend. And okay, see you sometime soon. Bye-bye.
Awesome! Congratulations! Thank you so much for watching this video end to end. On this particular channel, you will find everything that it takes to upskill you to become a data scientist. We have the 100% proven recipe. Check out the goodies over here, the workshops, the programs, and there's a number right here. Feel free to call me and I'll be very happy to help you with your journey in upskilling yourself and becoming a data scientist. Hit the subscribe button, click on the bell icon. Just make sure that if you like this particular video, don't forget to like it and follow us socially. I'll be there helping you out with how to make that transition happen for you.
Log on to Grey Atom's learning platform to unlock more content. Subscribe to our channel and hit the bell icon for regular updates.